Okay, so looking at either of these, really, we set them to live for a second plus or minus a half of a second. So many of them disappear while they're in the air, as we can see here. And just so you know, when we render these, the points themselves will have a size. They won't all be this fixed size like this, but we'll eventually make a size based off of how old they are. Much like how we had the density be driven by how old they are, we'll also make them start large and then get small before they disappear to kind of ramp into that. The thing is, a lot of these points land on the ground, like so. If they suddenly just get, it's one thing for a point to get smaller as it moves through the air, especially as it trails smoke, because it just seems that the point is dissolving through the air. A point that's landed on the ground probably shouldn't really be dissolving too much. I mean, maybe it's like settling into the ground a little bit, so we could tolerate some of it, but we probably don't want all of the points to disappear anyway. At the same time, as you've seen with how long it can take to do the simulation, we also don't need to have these points on the ground keep colliding with the ground, because that's what's happening. The points, especially if we decide to keep these points and not have them disappear, they're going to add even more overhead to our particle sim by continuing to collide on the ground every frame. So we can fix that. I mean, I wouldn't be telling you if we couldn't fix it. So let's fix it. To do that, I'm going to turn off for a moment the building thing itself, because I want to be able to, again, iterate on this quickly. Our main target really is these points all disappearing on the ground. So first thing we can do is say, on the pop solver itself, turn on this thing called sleeping, auto sleep, which basically says when you're not moving that fast anymore for a short amount of time, you can become asleep. And we'll make the sleeping color be white so we can actually see it. So you can see some of these points turn white, but they still disappear anyway because they're still aging. The way aging works, the way that these points get deleted, essentially is, if I show you in here, you don't have to do this, but just so you can see, they have an age, which is how old they are, and they have a life, which is how they're allowed to be. Once that is met, it gets deleted. It gets marked as dead, and then the particle solver will remove it. So basically what we want to do is say, those points that are now sleeping, let's have them be forever young, because they want to be forever young. So if we go here, I can say, make everything not age anymore, essentially by subtracting back out the amount of time that has passed. Now I only want to do it for the ones that are asleep. And the way sleeping actually works is that it's not called sleep, it's called being stopped. So put at stopped equals 1. Like so. So whatever we do in here will now apply to the things that have been marked, again, quote unquote asleep. Even though they're stopped, actually, they still collide though. So what we can do is say, first off, the age. Every frame, every time it does a solve, every substep really, it's adding to the time. It adds to the age. There's actually a built-in attribute though that's called capital time, capital inc, time increment. So what I'm saying here is the age equals itself minus this. That's what minus equals means. It's the same as saying age equals age minus that. But it's just fancier to do this. Actually, now it got me thinking about it the other way. Minus equals. Yeah, that's how I like to do it. Anyway, so age equals age minus time inc. And time inc is the amount of time in seconds that has passed since the last substep. So by default, when we're only doing one substep, like so, it's just going to be 1 divided by 24. It's 1/24 of a second. But if we ever did increase these substeps, time inc would also get smaller and smaller. So that's good enough. The other thing we want to do here is there's a string actually. So s at collision ignore, and we're going to say you should not actually collide with, well, anything. So do a star here. It's in quotes because it's a string, but what we're actually setting it to is this star. The star, the reason why it's a string is because it's referring to other dynamics objects. So this is a dynamics object, the ground plane, and this is a dynamics object, the static object here. So by star, it basically means no matter what it's called, you're not colliding with that anymore. And only do these things, of course, when you are marked as asleep. So if it turns back on, and I press play, I should see those things fall asleep, but never disappear. Uh-oh, I didn't mean to turn on the static object. That'll make it slow again. There we go. So we can see they're being marked white, and hopefully, most of them at least, shouldn't disappear. And as you can see, that's exactly what's happening. Furthermore, if I turn off the coloring, the sleep coloring here, they should actually retain the same colors they had when they landed, because they essentially are no longer being aged, or rather they are being aged, but then we're immediately subtracting back out the new time that has passed. So you might be wondering, well, why are some of them disappearing? Some of them are disappearing because they didn't reach the sleep state before they got culled. You know, we might instinctively look at this and feel like, well, they made it to the ground, and those are the ones I want to keep. But as long as they're still moving a little bit, they didn't actually get a chance to fall asleep. And it's only the asleep ones that are, you know, staying forever young and not doing the collisions anymore. So I would still say, though, the vast majority of them remain. And that should be enough, because if they were so close to being culled anyway, then they're probably already going to be very small in our renders, and we really won't notice. We can always just treat them as though they had sunk into the ground. If you really want to be a perfectionist, or really, if not perfectionist, but just you want to have every one of these points near the ground remain, instead of having it not age just the sleeping ones, you could say have it not age any particle that is near the ground. Say its p.y component is less than some threshold that would keep it towards the ground. So yeah, because again, this is waiting for the sleep. At any rate, I think this will look fine, and this is one of the many things that we can always tweak later if we don't like that. But I think this will be fine, so let us cache it and then review it. As you probably noticed before I did, forgot to turn the building collider back on. I was wondering why I was running so fast. So there you go, back in action, and let's recache this. Cool. So that should look pretty much the same as before, but you know, with the added benefit of the particles. Oh my god. The particles not disappearing as much on the ground now. So I'm just going to make a little flipbook and we can review, and then one more little visualization thing I want to do, and then we'll move on. There you go. So that's pretty cool. Bam. So again, we got the points all staying on the ground, more or less. Some of them disappear, but most of them stay, and the ones that disappear are probably quite small anyway. Sweet. I'm going to close that. The one last little visualization that I wanted to show you is regarding that last thing about the points disappearing and their relative sizes. So if I were to take a clip here, I'm going to move it up off the ground a little bit, change this to the other side. So here's all the points as they are landing just below this ground plane here, or this clipping plane, I should say. I'm going to say take a sphere. This is just temporary. And again, you don't even need to do this. Just watch mine. Copy the points. You know, when we render this, that's essentially what's going to happen. The mantra is going to render these as points. And these points are too big. P-scale is how they will actually be modified. So P-scale, let's say, equals 0.01, so that'd be much smaller. Maybe that's too small. Let's start it at that for now, just so we can see. And I also want to say, we want to use the age again. We want to use the age and life thing. So I'm just going to say n age, which is age divided by life. I'll just say 1 minus that. That way it starts off big and then becomes small. Something like that. So you can see how they land, And some of them get smaller before stopping, and then that's pretty much it. But that's the idea. And again, from a certain distance, they will more or less look like points. They'll just be, some points will be larger than others. So that's what we're shooting for. That's where ultimately where we're going to end up in the render. I just wanted you to appreciate that now while we were doing it. Cool. So on to the actual volume sims.